This is the solution for question 3a in homework 3. The first thing we should notice is that the equation is written in a way that suggests that the equation might be an exact equation. So I'm going to rewrite this in the form m of x comma y dx plus n of x comma y dy equal to 0. So that means that I have y plus natural log of x dx minus x dy is equal to 0. So in order to check if the differential equation is exact, what I need to do is find the partial derivative of m with respect to y and the partial derivative of n with respect to x. The derivative of m with y is 1 and the derivative of n with x is -1. So the equation is not exact. Not an exact differential equation. So our next possibility is that maybe there exists an integrating factor. This is some function such that when I multiply the original equation, I'm going to call it equation 1, when I multiply the original equation by this integrating factor mu, it becomes an exact equation. So the formula to find such integrating factor is m that multiplies the partial derivative with respect to y of the natural log of mu minus n, the partial derivative with respect to x of the natural log of mu is equal to the partial derivative of n with respect to x minus the partial derivative of m with respect to y. Now I already have these two derivatives and I have the suggestion, the initial suggestion, that mu is a function of x. That means that the partial derivative with respect to y is 0. And it also means that the partial derivative, actually any function here that would be like that, the partial derivative with respect to x becomes a total derivative because mu depends only on one single variable. In this case that would be x. So the equation, I'm going to call it equation 2, simplifies to the following. I have n is negative x, so negative n, that is positive x, that multiplies d over dx of the natural log of mu, and this is equal to -1 from partial derivative of n with respect to x minus 1 for the other derivative, so it's -2. So we can reorganize this. We can actually solve this by separable variables. And what we get is the following. The integral of the total derivative of the natural log of mu is equal to -2 over x dx, the integral of this. Calculating the integrals, well, here I have the integral of a total of a complete differential, and that means that I just get the function inside the complete differential, In the opposite, on the other side, I have -2 natural log, in this case of the absolute value of x, plus, I'm going to write it as -2 natural log of the absolute value of k. Combining the logs, I have that mu is equal to k squared x squared. Which is indeed a function entirely of x. Now we can use this integrating factor and multiply equation 1. This is going to be equation 3. So multiplying one by 3, what do we get? Let us copy that function, that equation, I multiply these by 1 over k squared x squared. And this is equal to 0. Obviously, this is only possible for x different from 0. But we already knew that from the fact that we had a natural log of x here. So this implies automatically that x is different from 0. And so does this, the fact that I send the x dividing. So very good. So what happens when I multiply here? So I'm gonna get now that y plus the natural log of x over k squared x squared dx minus 1 over k squared x dy is equal to 0. So I have a new function m, which I'm going to call m prime, and that is y plus natural log of x over k squared x squared, and I also have a new function m prime that is equal to -1 over k squared x. And well, the partial derivative of m prime with respect to y is equal to 1 over k squared x squared, and the partial derivative of n prime with respect to x is equal to 1 over k squared x squared. So as you can see, the new differential equation is exact. What does that mean? Mu of x times the original times m dx plus n dy is exact. Well, that means that there exists a function u such that the following is true. Well, this is always true for any function of x and y. But we're going to pair this with our differential equation here. So that means that partial of u with x is equal to m prime, where m prime is obviously mu of x times m, and well, partial of u with the y is equal to n prime. Um, from there, using the fundamental theorem of calculus, for functions of two variables, we have the following. U will be equal to the integral from x naught to x of m prime of t comma y dt plus some function of y and y alone. Substituting the values for the function m prime is equal to y plus natural log of t over k squared t squared dt plus some function of y, which at this point is unknown. How do we integrate this equation? We have a natural log and it is divided by t squared. So probably the best way to go about it is to integrate by parts. I'm going to copy this integral and we're going to solve it by parts. So let u equal, not u, let f equals to natural log of t. Then the f is equal to 1 over t dt. And I'm going to have that dv is equal to 1 over t squared dt, and v is equal to negative 1 over t. Now, when we integrate, I'm obviously integrated only the second part, so I'm going to get rid of that one. We don't need that one right now. That is much easier. And I'm going to call it integral 1. So integral 1 is equal to negative natural log of t over t from some x naught to x, and would be minus the product of these two functions. So that's going to be minus the integral of the product of those two functions. That would be 1 over t squared dt. I'm not going to evaluate that just yet. I'm going to leave it indicated for now. This is going to be 1 over t negative, and of course plus some constant, but we don't need to write it since it's going to be absorbed in the function phi of y. Integral then y plus natural log of t over t squared k squared t squared dt. This is equal to 1 over k squared times the integral from some x naught to x of y. The y integration is with respect to t, so the y is a constant. We can bring it out of the integral, plus the integral of natural log over t squared, which we call it I1. So that means 1 over k squared times negative y over t plus minus, in this case, natural log of t over t plus 1 over t. All of this from some x naught to x. Now, we have a little problem. Basically, when t is equal to 1, this term vanishes, this term becomes 1, this term becomes negative y. Okay, I'm going to follow that, and we're going to see why that will be a problem. So I have then that the integral of x naught equals to 1 all the way to x is of y plus natural log of t over k squared t squared with respect to t is equal to 1 over k squared times negative y over x minus, I could probably factor out the 1 over x, negative y minus natural log of x minus 1, and all of these minus negative y. This one is 0 and this one is simply negative 1. So reorganizing that and making it have a common denominator, I am going to have negative y, I have a positive xy here, xy minus y, I have a plus x minus natural log of x minus 1. Now, u was equal to this very integral plus phi of x. So that means that u is equal to x y minus y plus x minus the natural log of x minus 1. All of this divided by k squared x plus a function of y. And we're going to call this one equation 4. And we're going to do basically the same thing for n prime. We have that u is equal to the integral from y naught to y of n prime of x comma s, the s plus a function entirely of x. When we substitute the values of n prime in here, where is my n prime? Negative 1 over k squared x. I have that the integral from y naught to y of negative 1 over k squared x, the s, this integrand does not depend on s, so I can bring it out of the integral, and I get the very simple result and I need to think about a value of y naught that will be useful. And since we only have one term in s and it is on the numerator, I can make y naught equals to 0, and I will make that term go away. So I have then that u, function u is equal to negative y over k squared x plus a function entirely of x, and I want to call this one equation 5. And well, the idea is that I need to compare that equation with this one here. I'm going to copy the equation so that we can compare them more easily. So I have this thing here, y, negative y over k squared x, and this is exactly where my problem will be. I can only add a function entirely of x. So what do we have? We're gonna first write down the common terms. So there's only one common term. And it says here that I can add a function of x. So adding a function of x, that will be 1 over k squared from this one here, minus natural log of x over k squared x minus 1 over k squared x. Covers those three. I already have that one. This is the problem. That is not a function of x, and it's also not a function that is included in my equation 5. So this shows the danger of choosing the value of x naught poorly. So we go back in here and we analyze how that happened. Well, basically, when I choose x naught, it needs to be something that will either give me a constant or 0. I cannot end up with a function of y. So what do we need? Well, what we really need is to choose x naught in a way that will make this term 0 or a constant. So let's take a look. We need negative y over x naught minus natural log of x naught. We're gonna make x naught the common term minus 1. We need this to be equal to k or 0. 0 ideally, that makes things easier, but k is also alright. Basically, I need natural log of x naught is equal to negative y minus 1. There you go. So that means that x naught is equal to e to the negative y minus 1. If I choose that value for x naught, then the function itself will cancel. Okay. So let's say that we do indeed choose that. So this was my integral 1. No, this was u minus phi of y. So that means that u is equal to 1 over k squared x that multiplies negative y. I want to factor out the negative as well. So I get y plus natural log of x plus 1. And this minus, and when I evaluate this whole thing at this point, this thing cancels, so I don't need to worry about it. And we end up with this plus some function of y. Now that should be my equation 4. Now let's compare that with equation 5. We already had an equation 5, which is right here. I don't need to make any changes on that one because I did not have the problem of choosing the appropriate value for y naught. That only happened in x naught. So when we compare those two equations, I see that the first term is negative y over k squared x. So I write that because it's the common term. According to equation 5, I can only add a function of x. And luckily for us, 1 over k squared x times natural log of x plus 1 is a function of x. And I don't have any other function of y to add in this case, so this is the complete equation. Now what we started with, though, the first equation was the u is equal to well, the transform equation after multiplying by the integrating factor and prime the x plus y prime the y. This was equal to 0. Okay, so if the u is equal to 0, then that means the u is equal to a constant. So my answer should be something like 1 over k squared x multiplies y plus natural log of x plus 1 is equal to alpha. Might as well send this to the opposite side. So it's going to be negative alpha k square x. And well, alpha k squared is simply another constant. I'm going to call it beta. And this right here is my solution. I could solve for y. It's actually not that difficult in this case. So y is equal to negative beta x minus natural log of x minus 1. That would be my explicit solution. So in order to test whether this is indeed a solution to the differential equation, I need to find the y, and well, that is going to be negative beta the x minus 1 over x dx. I can multiply everything by x and I get x dy is equal to negative beta minus 1 dx. And now let's take a look at this. That is not true. Beta x minus 1 dx. I have the negative beta x, I have negative 1. I'm missing the natural log. So really this term here is equal to y plus natural log of x. So I have that x dy is equal to y plus natural log of x dx. And reorganizing that, I get that y plus natural log of x dx minus x dy is equal to 0. I have y plus natural log of x minus x dy. So it is indeed a solution.